Hello, it's me again. So, we're going to look at Chapter 7 today, which is an introduction to alkenes, and then the really big chapter, Chapter 8, goes further in more detail about alkenes, and I'll look at that when we get back to class, when I get back to class on Monday. So first, let's look at some properties of alkenes. So alkenes are hydrocarbons that contain a carbon-carbon double bond. Alkenes have the general formula CnH2n, so that's different from alkanes, which is CnH2n plus 2, because we have two less hydrogens now because of the pi bond. Alkenes are often referred to as unsaturated hydrocarbons. Remember we talked about this before. It's talking about being saturated with hydrogen. It has the maximum number of hydrogens possible. Alkenes do not have the maximum number of hydrogens possible, and so they're referred to as being unsaturated. What we're going to look at now is what's known as calculating the index of hydrogen deficiency, also known as degrees of unsaturation. So this is going to be a number that we can calculate. It'll give us a number that represents the number of pi bonds and or rings in the structure. So this number will be the total of pi bonds and rings in the structure. And this is going to be very useful, especially when we get to spectroscopy, when we have to determine or deduce an organic structure looking from different spectroscopic techniques. So this is the formula. Double the number of carbons. So I'm going to put IHD. Double the number of carbons. Add any hydrogens. Subtract number of hydrogens and halogens. And plus 2 and divide by 2. So plus 2 divided by 2. So a lot of organic compounds just have carbon, hydrogen, and oxygen present. And so that would simplify to twice carbons, subtract hydrogens, plus 2 divided by 2. So oxygen does not factor into that formula. Okay. So let's look at some different examples. Look at C6H6. So the IHD there should be twice the carbons. So 2 times 6, subtract hydrogens, plus 2 divided by 2. So remember your hierarchy, you have to go for addition subtraction, you go left to right. So 2 times 6, do multiplication division first. So 2 times 6 is 12. 12 minus 6, 6, 6 plus 2, 8, 8 divided by 2, 4. I've seen some students make a mistake by saying like 2 times 6 is 12, and they do 6 plus 2 over here and say 8, and 12 minus 8, and they'll get the wrong answer. So remember, 2 times 6 is 12, then you have to go left to right. Let's look at another one. C3H6O. So 2 times 3, 6 minus 6, 0, plus 2, 2, divided by 2, 1. So that tells me I either have a pi bond or a ring in my structure. This one up here tells me I have a combination of 2 pi bonds, 2 rings. It could be 3 pi bonds and a ring, or it could be 4 pi bonds. So it's a combination of pi bonds and rings in your structure. if you're given the structure, it's easy to figure out. So like if you look at benzene, which is C6H6, if you're just given that structure, you say, okay, I have 3 pi bonds in a ring. So just from looking at the structure, I'd know it'd have an IHG of 4. Same thing with acetone. And just looking at that structure, I know I have 1 pi bond, so IHG of 1. Likewise, if we looked at cyclohexadiene, I just have 2 pi bonds, so that's 2 pi bonds in a ring, so that's IHG of 3, just from looking at the structure. If I did acetylene, triple bond, 2 pi bond, so IHG is 2 there. Okay. So let's look at some problems from the textbook. Look at some of these down here. So this is 7-2. I'm going to look at D. So that says C9H16 BR2. So C9H16 BR2. So 2 times 9, subtract 16. Now I have a halogen, you subtract halogens. Subtract 2 and plus 2 divided by 2. So I have 18, 2 times 9 is 18, minus 16 is 2, 2 minus 2, 0, and then I have plus 2, 2 divided by 2, 1. So IHG of 1. So that tells me I either have 1 ring or 1 pi bond. So I could just draw out a structure like 9 carbons, put 2 bromines on it someplace, and put a double bond in it someplace. I know I'd have that formula. Let's go ahead and look at this next one. Let's look at E. So I have C10 H12 N2O3. So 2 times 10 minus hydrogens, minus 12. 2 nitrogens, you add nitrogen. So subtract halogens, add nitrogens. Ignore oxygens. And then just plus 2 divided by 2. So 20 minus 12 is 8. 8 plus 2, 10. 10 plus 2, 12. 12 divided by 2, 6. So IHG of 6. So now I have a combination of 6 pi bonds or rings. So that could be 3 triple bonds, it could be 6 double bonds, it could be a triple bond, 2 double bonds, and 2 rings or something. It's just a combination of all the pi bonds and rings that are possible. Let's look at 7-3. So here I have the structure of diazepam, marked it as an anti-anxiety medication under the name Valium. Has 3 rings, 8 double bonds in the formula C16H Cl(N2O). Now I asked how many hydrogens does it have? Now I'm given the structure here, so you could count the hydrogens and figure out your answer. I'm going to act like we do not see the structure here. I'm going to calculate how many hydrogens we have. So I know my formula for IHD is twice the carbons, subtract the hydrogens, subtract halogens, so subtract 1, plus 2 for the nitrogens, ignore oxygen, so then I just plus 2 divided by 2. And I know diazepam has 3 rings and 8 double bonds, so that's 8 pi bonds, so 3 plus 8, I should have an IHD of 11. So I'm going to set that equal to 11. So now I'm going to solve for my number of hydrogens. So I have 32, subtract hydrogens, multiply both sides by 2. Gather like terms on both sides. Be harder to do. So solve for H then. So I have what? 10. 10 minus 1, 9, plus 2, 11, plus 2, 13. So I have 13 hydrogens in that structure. Okay. Now we can check our answer 2 ways. We can check our answer by just plugging in 13 up here, make sure that comes out to be 11. Or I can go ahead and just count, since I'm showing the structure, I can go ahead and count and make sure that's 13. Let's go ahead and count. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So yep, I have 13 hydrogens. So we're going to go on and look at what's cis and trans isomers and alkenes. So we've always saw cis and trans isomers in cycloalkanes, where they're on the same side of the ring or opposite sides of the rings. Same thing with double bonds, except now we're looking at double bonds. You can have substituents on the same side of the double bond or opposite side of the double bond. And the reason you have these various stereoisomers, because when you have a single bond, you can rotate all the way around that single bond. When you have a double bond, it's locked into position, so you can't rotate it. And so if you have 2 things on the same side of your double bond, they're locked in that position. Makes it different from if they're on opposite sides then. So let's look at some examples. These are both 2-butene. So if I look at my C double bond C, I'll see that my 2 methyl groups are on the same side of that double bond. So that means this structure would be cis. Here they're on opposite sides, So that structure would be trans 2-butene. If one side of the double bond contains two identical groups, cis-trans isomerism is not possible. So in this example, this carbon, two of the exact same groups. So you can't have cis-trans isomers because if you switch those two groups around, it's the exact same thing again. So two the same groups are attached, two identical groups are attached to the one carbon double bond. Cis-trans isomerism is not possible. If the alkene contains 3 or 4 substituents, a new system must be used to designate between isomers. So if I look at these two compounds, so here the bromine is on the same side. Well, I should change the molecules up. Keep one side the same. So here the bromine is on the same side as the methyl group. Here the bromine is trans to the methyl group. But so we need a new system to indicate cis and trans in this case, because what you're talking about, if you call this cis, what two things are you saying are cis to one another? Are you saying the methyl group of bromine or the chlorine and the ethyl group? So we have to have a way to designate what two groups are you saying are on the same side, what two groups are you saying are on the opposite sides. Before we get into that though, this new system, we're going to go and look at some homework problems from the book. So if we look at this problem, this is 7.7-9. It says, which of the following compounds can exist as a pairs of cis-trans isomers? Draw each cis-trans pair and indicate the geometry of each isomer. So if I look at the first one, it says CH3, CH double bond CH2. I have two hydrogens on one side, so that one cannot exist as cis and trans. If I look at the next one, CH3, 2, C double bond C, HCH3, so again, two methyl groups attached to that carbon. No cis-trans isomerism possible. If I look at the next one, I have an ethyl group and a hydrogen attached to one carbon, other side hydrogen and methyl group, so that one I can have cis-trans isomers. ethyl and the methyl could be on the same side, or they could be on opposite sides. So look at D, two methyl groups on this side, no cis trans possible. E and F are going to be very similar. They have chlorine and hydrogen, so that one can't have cis and trans. So the two chlorines could be on opposite sides, or they could be on the same side. So now we're going to go back and look at, okay, if we have 4 different substituents there, how can we indicate the stereochemistry? So the example I gave, I had a bromine and chlorine attached to one side. The other side I had a methyl and an ethyl group. So I'm going to indicate the stereochemistry of this. So we're going to use this new rule, and it's going to be using what's known as E and Z designations. So to do this, we assign priorities to the groups attached to the sides. So at this point, you would have seen this using these same rules when we looked at stereochemistry during the R and S configuration. So it's the same rules as those con and gold pre-log rules. And so the E designation, you assign priorities to the groups, and then you rank them, whichever one's highest priority on each side. And if the 2 higher priority groups are on the same side, it's Z. If they're on opposite sides, it's E. So just to review con and gold pre-log rules, rank the first atom attached directly to the double bond according to the atomic number. The greater the atomic number, the higher the ranking. So if I look over here, bromine and chlorine on one side, bromine, higher atomic number, higher priority. Other side, carbon, carbon. Okay, so they're the same. So if a difference can't be reached by ranking the first atom of this substituent, look at the second, third, and fourth atoms away from the double bond until a difference is found. And so, in this case, I look at the second atom, another carbon, no other carbons here. So that would be your highest priority. They're on opposite sides, so that would be an E configuration. And also as a review, remember multiple bonded atoms are equivalent to the same number of single bonded atoms. So if you have C double bond O, that's like a carbon bonded to 2 oxygens. If you have a C triple bond in, that's like a carbon bonded to 3 nitrogens. And so if you only look at the number of them if you're comparing the same atom. And so like 2 oxygens at the second position is going to be a higher priority than 1 oxygen at the second position. Okay. But like 3 carbons is not higher priority than just a single oxygen. You still go by atomic number, and then you just compare the number that you have of that atom if they're identical. So we'll look at an example and work some problems. Assign E or Z configurations to a double bond of the following compound. So if We'll look at this one. I have a hydrogen, comparing that to a carbon. So carbon's highest priority on this side, other side, carbon, carbon. Same, go to the next atom, oxygen, in this case, 2 carbons. Oxygen, the higher atomic number though, so it's the highest priority. Highest priority group's on the same side. That's a Z configuration. So let's look at some homework problems. So this is 7-11. So it says, which member in each of the following sets rank higher? The first one, I have a hydrogen and a CH3, so first atom, H is carbon, carbon higher atomic number, higher priority. Next one, Cl or CH2Cl, first atom, chlorine, carbon, so chlorine higher priority. Next one, first I have a carbon, CH2, CH2Br, you have a CH double bonded to a CH2. So first atom, carbon, carbon. Now I go next atom, carbon. Here I have 2 carbons because I have a double bond, so it's equivalent to 2 bonds to carbon. And so before I even get to the bromine, I have found a difference. It's 2 carbons, higher priority than 1 carbon. So the C double bond CH2 is higher priority, even though later on there's a bromine that has a higher atomic number. D, first atom, nitrogen or oxygen, oxygen higher atomic number. E, CH2OH or C double bond O, so first atom, carbon, carbon, next atom, 1 oxygen, here's 2 oxygens, so my C double bond O, higher priority. Go ahead and look at a few of these. So it says rank the substituents in each of the following sets according to the sequence rules. So I'm going to label my highest priority as 1. So it's the same thing we did when we did R and S configurations. So I'll look at this. I have carbon, oxygen, hydrogen, or chlorine. So I go to the periodic table. Look at these, all these atoms in the periodic table. See, chlorine has a higher atomic number, so it's 1. Then I look at oxygen, carbon, hydrogen. So oxygen would be 2, carbon 3, hydrogen 4. Next one, carbon, 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 carbon. So I go to atom 2, carbon, 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 oxygen. So oxygen would be 1, 2 carbons 2, methyl group would be 4. Next one, carbon, 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 carbon. Next atom, 3 oxygens, 1 oxygen, 1 nitrogen, 3 nitrogens. And so oxygen is a higher priority than nitrogen, and so I want the 3 oxygens going to be highest priority. Then I want just the 1 oxygen, okay, because it's still, even though this one has 3 nitrogens, oxygen's higher atomic number, higher priority. Okay. Last one, first atom, carbon, 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 carbon. Go to the next atom, carbon, 3 carbons, 3 nitrogens, 1 oxygen. Oxygen highest priority, it's 1. 3 nitrogens higher than 3 carbons. 2, 3, 4. So 7-13. Have to do some E and C configurations. So I'll look at one side, chlorine, carbon, chlorine higher priority. Other side, carbon, carbon, next atom, another carbon here. So in this case, they're on the same side. So that would be Z. Next one, this side, oxygen, chlorine. So chlorine, higher atomic number. Other side, carbon, carbon, next atom, carbon, carbon, next atom, another carbon. So that would be on opposite sides there. So that would be E. So if we look at this first one, let's go to this side first. So I have carbon, carbon, next atom, oxygen, 3 oxygens. That's highest priority. So the next side's a ring though. So I'm going to go around the ring one way. Here's my first atom. Here's my second atom. And then my third atom, I have a CH3 and a CH2. So I have 2 carbons 3 atoms away. I go around the ring the other direction. First atom's a carbon. Second atom's a carbon. Third atom is just 1 carbon. And so going around the ring this way is higher priority than going around the ring the other way because I get to that methyl group first. So that's your highest priority. They're on the same side. So Z. Next one, carbon, hydrogen, carbon, carbon, 1 nitrogen, 3 nitrogens, opposite sides. So E. So now we're going to look at alkene stability. So transalkenes are more stable than cisalkenes due to the steric strain of the 2 substituents being on the same side of the double bond in a cisalkene. Increasing the degree of substitution also increases the stability of an alkene. So the more alkyl groups you have attached to your double bond, the more stable it is. And so really when you look at cis and trans is when you only have 2 substituents. And trans is more stable than cis. But if you have like a tetrasubstitute alkene, it's more stable than a trans disubstitute alkene. So if we look at this though, I'm going to put tetrasubstituted, more stable than tri, more stable than trans di, more stable than cis di, more stable than mono-substituted. When I talk about degree of substitution, you're looking at what's attached to your C double bond C, but you're not looking at hydrogens. So this carbon has 1 attached to it, 2 carbons, 3 carbons. So that is a tri-substituted alkene. These problems here, I'm just going to tell which one is more stable in each pair. So if I look at this first one, and I'm looking at your C double bond C, so this has one other carbon attached to it. So that's a monosubstitute alkene. If I look at this carbon on this side of my double bond, I have two carbons attached to it. So that is a disubstitute alkene. So that one's more substituted, so it'd be more stable. If I look at B, disubstituted, but here the difference is cis and trans. Trans more stable than cis. So this last one, C, and I'm looking at my C double bond C. So here I have one carbon, two carbons, three carbons. So that's tri-substituted. Here the C double bond C, I have one carbon, two carbon. So that's just di-substituted. So tri-substituted, more substituted, more stable. So now we're getting to the last part of chapter 7. We're going to start looking at reactions. So we had an overview the last chapter where we talked about nucleophiles and electrophiles. So we saw the types of nucleophiles are something that was electron rich. So something with a minus charge, extra electrons, lone pair of electrons, or the pi electrons of a double or triple bond. So the carbon-carbon double bond is electron rich and can donate a pair of electrons to an electrophile. And so this will be our first organic reaction that we're going to learn. Okay, and we're going to look at all the details of this organic reaction. And then chapter 8, we're going to look at a lot more chemical reactions. A lot of them will be very similar to this as far as mechanism is concerned. So I have a C double bond C. So here I have hydrogen halide. Halogen electronegative pulls electrons towards it. That means it has a partial positive charge. And so the electrons in your pi bond add the hydrogen. Those electrons in that bond will go up onto the halogen because it's electronegative and accommodate that minus charge, those extra electrons. So the product then that we'll see overall will be an H adding to one side and the X adding to the other side. So if we look at the complete mechanism, the H adds to one side, positive charge at the other side. And the hydrogen halide, the halogen, will attach to the carbon. And I'll get my product. So let's look at a specific example. So this is like the generalized equation. So how will you see this written out? So this may be how you see it. So hydrogen adds to one side, bromine adds to the other side of my double bond. You may also see it written as two different components where you have your acid source, something that pronature double bond, and then you have some kind of nucleophilic source, potassium iodide. Remember, in organic chemistry, anytime you have a metal and non-metal minus charge. So it's like an I minus, good nucleophile. So your iodine will attach. H adds to one side, iodine adds to the other side. And you'll notice I put the iodine here. Why didn't I put the iodine down here? Okay. So that's what we're going to look at next. The addition of HX to alkenes is what's known as regiospecific. The halogen attaches to the carbon more alkyl substituents. This is what's known as Markovnikov's rule. And we'll see different reactions that follow Markovnikov's rule. Some will follow anti-Markovnikov's rule. So Markovnikov's rule just states it's going to go to the most substituted position. So if I'm looking at this C double bond C, it has one carbon here, no other carbons attached to the other side, so this one's more substituted. It has more carbons attached to it. Like this carbon has, say, two carbons attached to it, this just one. And you can put the HBr, you can say plus HBr, you could see it written over the arrow as well. But again, H adds to one side, bromine adds to the other side. Bromine goes to the most substituted position. So if I'm looking at these two carbons, this one's attached to one, this one's attached to two, this is the most substituted position. So that would be my product. The reason this takes place is because the hydrogen adds to the alkene to produce the most stable carbocation. And so when it adds, we see how the intermediate is a positive charge on carbon. Carbons are electropositive, so you know halogens are electronegative and through an inductive effect pull electrons away. Well, carbon alkyl groups can actually push electrons towards a positive charge. So if you have a positive charge through an inductive effect, they push electrons towards that positive charge. So the more alkyl groups you have, the more inductive effect you see with the alkyl groups pushing electrons towards that positive charge, stabilize that positive charge. I love this complete mechanism. Double bond adds hydrogen, kicks off the chlorine, so the positive charge can go here or here. Well, if it goes here, there's only one alkyl group attached to it. If the positive charge went here, it has three alkyl groups attached to it. So that's going to be a lot more stable. You have three alkyl groups pushing electron density towards it, making it more stable. So that means the hydrogen goes to this least substituted position, creating a positive charge at that most substituted position. And then your chlorine can attach, and you get your butyl chloride. So this intermediate stabilizes what's known as inductive effect. So we saw resonance effects before, this inductive effect. So the greater the substitution of the carbon, the more favorable the formation of the carbocation, and the reaction rate will increase. We're looking now at some problems from the chapter. here I have to predict the products of some reactions. So if I look at this first one, HCl adding to a double bond. So in this case, it'd make a secondary carbocation in either position. So this carbon's attached to 2, this one's attached to 2. So that means chlorine could go to either place, but it's still the same. Either way, you get chlorocyclohexane. So I'll just put my chlorine at one of the positions. On this next one, this carbon is attached to 3. This carbon's only attached to 2. So my bromine will attach to that most substituted position. So hydrogen's the least substituted position, bromine most substituted position. So if I look at this next one, now I have H2O, H2SO4. We haven't covered that reaction yet. But if I look at the hint down, it says addition of H2O takes place. So if HCl, H adds to one side, chlorine adds to the other side. HBr, H adds to one side, bromine to the other side. H2O, H would add to one side, OH to the other side. And just like with the addition of HBr, HCl, the OH goes to the most substituted position, where he follows Markovnikov's rule. So OH, most substituted position. Look at the next one, D. There's my 2 carbons in my double bond. This carbon has 3 carbons attached to it. This just 1, so the bromine would attach here. CH3, bromine. Now this we're going backwards here. We're saying, okay, we want to make this product. What alkene do I start with? So just another way to see if it's the same problem. You just have to think about it a different way. So I look at this first one. I have a bromine attached to a cyclopentane ring. So I know H adds to one zinc, bromine adds to the other side. I know wherever the carbon that has a bromine attached to it, that had a double bond on it before. So you add a double bond between that carbon and the adjacent position. Next one, I have an iodine going to the more substituted position. So I have 2 unequivalent. So if I could put the adjacent position here, it's the exact same thing, but it's different than going out there. So I can put my double bond there. See it? Or I could put my double bond out there. Both of those would work. You want to check and make sure both of them work. Double bond there, you can't tell. Okay, so if I'm looking at this position here, so here's my C, double bond C, This one has 3 carbons, 1 carbon, so most substituted, that's where my iodine goes. 3 carbons, 2 carbons, so again, that's where my iodine goes. And so both of those would give me the same product. I shouldn't say plus, I should say or. Okay, so either one of those would be correct answers. You use either one of those alkenes. I'll look at the next one. Here's the carbon with the bromine on it, so I'll look at forming the double bond between it and the adjacent position. So that's adjacent position to the left. I can look to the adjacent position to the right. Now in this case, one of these alkenes, one of these answers is better than the other. Okay. So if I look at this first one, they're equally substituted. This carbon's attached to 2, this carbon's attached to 2. So that means the bromine could go to either position. The bromine could go here, or the bromine could go there. Okay. We would want the bromine to go to this position, but if I did that reaction, I'd get a mixture of products, so that wouldn't be as synthetically useful. But if I look at this next one, again, they're equally substituted. This one has 2 carbons, this one has 2 carbons. But if I put my bromine here, I get 3-bromohexane. If I put my bromine here, I get 3-bromohexane. So it can go either position, but it gives the exact same product because that alkene is symmetric. So that gives you a single product. So that's the alkene that you would want to use. If I look at this last one, so if I look at that first one I drew, okay, so again, I just looked at my 2 possibilities. So this one, this side, 3 carbons, this side, 2 carbons. So this is the most substituted position. So that's where your chlorine would go. That's not where it is in the product. So that's even worse than up here using this one, because this one you at least got some of your desired product. Over here, this carbon has a 2 attached, just 1, so all of your product would go here, most substituted position. That's the alkene you'd want to use. Last thing we're going to look at in Chapter 7 is what's known as a carbon-cation rearrangement. So we have seen that this reaction takes place through a carbocation intermediate. So let's look at an example so I can illustrate this. So I'm looking at this reaction. Okay, so I'll go into the lab and I do this reaction. So what I expect to get we be that product. The chlorine adding to that most substituted position. Okay. But when I go into the lab and actually do this reaction, that's not the only product I get. I see a product looks like this as well. Okay. Where the chlorine is attached to this carbon. So how did that happen? That carbon is not even a part of the double bond. So how did the chlorine end up over there? So to answer that, I have to look a little bit closer at the mechanism. I'm just going to redraw this. So I know my mechanism. Hydrogen adds. Hydrogen adds to the least substituted, positive charge to the most substituted. So I have this intermediate, which is a secondary carbocation. So when you see a rearrangement is when an adjacent position is more substituted. So like in this case, I have a secondary carbocation, but the carbon right next to it is a tertiary carbon. So what you see, it rearranges to form a more stable carbocation. So this hydrogen shifts over to that carbon, and that's termed a hydride shift. Because the hydrogen with the electrons are moving to that adjacent position. So that hydrogen moves over. Creating now a tertiary carbocation that's more stable. So then that's how you see the chlorine attaching to that position, that carbon that was not even originally part of your double bond. So that's when you'll see this hydride shift, as if you have a carbocation and the adjacent position is more substituted. You see a hydrogen shift over. You could also see a methyl group shift over. If you had a methyl group here, if you didn't have any hydrogens to shift over, you could actually see a methyl group shift over. That's called a methyl shift. Let's look at some problems from your homework to finish up this chapter. So it says, on treatment with HBr, final cyclohexane undergoes addition and rearrangement to yield 1-bromo, 1-ethyl cyclohexane. Using curved arrows, propose a mechanism to account for this result. So I'm going to start out my mechanism, just like all the other mechanisms. Electron-rich source, pi bond, adds a hydrogen from my HBr, where I have a partial positive on that hydrogen. So then I'd have a positive charge on the most substituted position. But now I have a secondary carbocation position adjacent to it is tertiary. So I'll see that hydride shift. A lot of times, instead of showing the mechanistic part of the hydride shift, you'll see just hydride shift written. So then my bromine that I have can attach to my positive charge to account for the observed product. Let's just look at one more problem. So here we have to show structures of the carbocation intermediates. Let's go ahead and do that. So if I look at this first one, so carbon's here, it's attached to 2, this carbon's attached to 3, so my positive charge would go there. So on your online homework, also make sure you pay attention to what the question is asking, because you may see this written down and you think, I have to draw the product of that, so you add your bromine to it, but if you read the question, you'll see that it says, draw the structure of the carbocation intermediate. So it's looking at you to draw the intermediate and not the final product. So if I look at this one, this carbon has 3 attached, this one just 2, so my positive charge would go there. So that's it for this lecture. So that's all of Chapter 7, and I'll see you for Chapter 8.